Back Chemistry 30. This is the EQ3.4 section, the auto-ionization of water. So we'll look at what that means and understand how H3O plus or H plus and OH minus are related. One of the most important chemical properties of water is its ability to be either an acid or a base. So it can act as a Bronsted-Lowry acid or a Bronsted-Lowry base. So in the presence of an acid, water will tend to act as an H plus ion acceptor, more basic. In the presence of a base, water would act as an H plus donor, so it is more acidic than the base. In fact, one molecule can donate one proton to another one itself. So if we take a look over here, we could have one of these H's leave its electron behind, be H positive, and of course attracted to the negative area of the water molecule and make the hydronium ion here and leaving a hydroxide behind. So it can actually transfer with another water molecule itself. And this is called the auto-ionization, so the ionization of water automatically. So the forward and reverse reactions are extremely rapid, and no water molecule remains ionized for long. At room temperature, only about 2 out of every 109 water molecules, which works out to be 1.8%, are ionized at any given time. So most water exists as simply H2O and H2O. But 1.8% of all water molecules will exist as hydroxide ions and hydronium ions for a short time. So thus, pure water consists mostly of H2O water molecules, extremely poor conductor electricity, but some of it does exist in ion form for a while. That leads us to the ion product of water. The equilibrium constant expression for the auto-ionization of water would be this, because if we look over here, liquid, aqueous. In the KEQ expression, remember we only include the aqueous substances or gases. So in this case, we only have hydronium ions and hydroxide ions in aqueous form. So yes, on the next page you see the term H2O is excluded from the equilibrium constant expression because we exclude the concentrations of pure solids or pure liquids since their concentration does not change as much as gases and aqueous substances. Since this expression refers specifically to the auto-ionization of water, we use this symbol Kw. So instead of KEQ or Kc, it's the water constant, or Kw. To represent the equilibrium constant, which is called the ion product constant as well, it is equal to 1.0 times 10 to the minus 14. So in any water solution, if I take the concentration of hydronium ions and multiply it by the concentration of OH minus ions at 25 degrees C, it's a really small amount, 1.0 times 10 to the minus 14. It tells us that very little of these exist. Since H plus and H3O plus are used interchangeably, we could just simply refer to it as this. Instead of H3O plus, just simply call H plus. H times OH, 1 times 10 to the minus 14. So if we have a solution in which we have equal amounts of these, and they multiply to give us that number, of course that's a neutral solution. We don't have more of H than OH, etc. In most solutions, however, the H and the OH concentrations are not equal. As the concentration of one of these increases, the concentration of the other one must decrease, so that again we have the product equaling 1.0 times 10 to the minus 14. So in a case of an acidic solution, that means we would have more H pluses than OH minus ions, and still multiply to give us that number, but we have more of one than the other. In a neutral solution, we would have to have both of them equal, and in a basic solution, our H plus would have to be less than OH, or OH is bigger than H plus, and again, multiply to give us that number. So if I look at the values of H and OH in a neutral solution, so if we're looking for this, H times OH, we know that they must equal to be 1.0 times 10 to the minus 14, and hey, we know that they must be equal, right? So if I call this X, I would have to call this X, because I know that they are going to be equal. So X squared is equal to 1.0 times 10 to the minus 14. And if I take the square root to isolate x, I get 1.0 times 10 to the minus 7 molar. So, which equals H, and also equals OH. So the concentrations of those must be equal in order for that to happen. All right, knowing that, I can look at these examples here. Indicate whether solutions of these are neutral, acidic, or basic. So I know that for neutral, H is equal to OH, which is equal to 1.0 times 10 to the minus 7 molar. So all I have to do is really compare my numbers to that, and I can tell what's going on here. So over here, if I have H being 4 times 10 to the minus 9, now be careful here. Some people see that 9, see that 7. Oh, this is bigger. But remember, this minus 9 means that this decimal is 9 places to the left, and this decimal is 7 places to the left. So we can see here that 4 times 10 to the minus 9 is less than 1.0 times 10 to the minus 7. Okay, so if my H solution is less than that, then we know that H is less than OH, because OH has to be much larger than that, because they must multiply to give us 1.0 times 10 to the minus 14. So OH has to compensate for the low amount of H. So therefore, basic. Look over here, 1.7, 1 times 10 to the minus 7 molar is equal to 1 times 10 to the minus 7. Then, H plus equals OH minus, therefore neutral. And then lastly, if I look over here, OH this time. OH. Now that number, this number compared to the neutral number, this is way smaller. That decimal is 13 places to the left. Therefore, it's less than 1 times 10 to the minus 7. Then, now this represents my OH. So OH must be less than H plus. So H plus has to be really large to compensate for the low amount of OH, because we know that they must multiply to give us this as a kW at 25 degrees C. So OH is less than H, or I can read this as H is bigger than OH, therefore acidic. All right, let's look at the next example. Calculate the concentration of H in each of the following. If I have a solution in which OH is this, or if I have a solution in which that, so let's take a look here. So H times OH must equal 1.0 times 10 to the minus 14. So if my H concentration, if my OH concentration is 0.010, okay, to solve for H, it's H multiplied by that. So all I have to do is divide by 0.010. And H plus is equal to 1.0 times 10 to the minus 12. Now, of course, we can see that, now I'm also supposed to say whether it's acidic, basic, or neutral. Since 1.0 times 10 to the minus 12 is, oh yeah, it's less than that neutral number, isn't it? So H plus concentration is less than OH, which must compensate for that amount. Therefore, basic it has to be. Okay, let's look at the other one. H times OH equals 1.0 times 10 to the minus 14. This time OH is 1.8 times 10 to the minus 9. So same thing here. To solve for H, divided by 1.8 times 10 minus 9. divide by 1.8 times 10 to the minus 9. And H equals 5.6 times 10 to the minus 6. And we can see that 5.6 times 10 to the minus 6 is larger than 1.0 times 10 to the minus 7. Because this is only 6 places to the left, whereas this is 7 places to the left. So then we know that H plus must be bigger than OH. OH has to compensate for the large value of H. Therefore, it's going to be acidic. Right, so that's how we do that. So we have this relationship up here, Kw, and then from there we know that for a neutral solution, H and OH must equal this for concentration. Then whatever concentration we have in our question, we can compare with that neutral concentration amount and figure out if it's acidic or basic. All right, you should be able to do the assignment now. We'll see you again.